Hello, everyone. So I'm Xiaoxuan from Meta. Today, I'm going to talk about the improvements we made to the Velox memory system in the past year to help the Prestissimo migration. So here's what I will cover in this talk. We first discuss about the memory-related problems we encountered during the Prestissimo migration, and then the key achievements that we made to addressing them. And then we next talk about take a quick overview of the Velox memory system to see how it works. Then we deep dive into the improvements we made in the three key areas, from performance, the query wound prevention, and the server wound prevention. So starting early last year, we are able to run most majority Presto batch query in Prestissimo and see very good reduction in the CPU time savings. But unfortunately, we see the query wall time is much worse than compared with the Presto Java. And through analysis, we find out one of the main slowness because of the slow memory arbitration. Then we heavily optimize the memory arbitration and the disk billing to fix the problem. And after that, Presto started migrating to a new hardware with much higher CPU concurrency and large memory capacity. And this lead to the CPU time regression compared with Presto Java. And through analysis, we discover the high lock contention from Velox own memory allocator is the main cause of the slowness. And we fix the problem by switching to JE-malloc-based memory allocator, which is better at handling high concurrent memory allocations. And the second half of last year, we started deprecating LBM queries and migrating the QRT query to Prestissimo. And this pushed our system limits. One main challenge is query running out of memory. And either due to that, we lack of sufficient spill coverage for spill operators, or we see unexpected memory growth from the non-spill operators. So we extended the spill coverage for spill operator and built a memory mechanism to cap the memory usage from the non-spill operators' physical problems. And during the Prestissimo migration process, we see the server wounds instance like either because the system is overloaded or some bad queries using excessive memory from non-Velox tracked memory system. It's like JE-malloc. So we built the generic memory pushback mechanism to handle the transient non-Velox tracked memory spikes. And in parallel, we keep improving the Velox stack to make sure all the significant memory allocation were made through Velox memory pool. And also for the non-Velox components, which are memory intensive, like the remote storage client we use in Meta, we built a throttle mechanism to prevent excessive memory usage when the client, either the client or the backend service in some unstable state. With this all improvement together, we significantly improved the reliability and the performance of the persistent running at Meta. Yeah, so next before we deep dive into the actual improvements, let's first take a brief look at how the Velox memory system works internally. So it makes up the 5 major components. The first component is the memory pool, which provides query memory allocation. So internally, it dedicates allocation to the memory allocator. It tracks the query's memory usage. The memory pool can dynamically grow its capacity by requesting more capacity from the memory arbitrator through a process we call a memory arbitration process. The next component is the memory arbitrator. The memory arbitrator allocating capacity for the query and also arbitrate the memory capacity among them. So memory arbitrator leverage the disk billing techniques to reclaim the used memory from the running queries if necessary. The next component is the data cache. And data cache provides in-memory cache for the frequent access data. It doesn't allocate memories through. It allocates memories through the memory allocator directly, bypassing the memory arbitrator and the memory pool, which means that the memory allocator needs to guarantee that the memory allocated to both query and the cache stay within a certain limit. The last component, when the memory allocator reaches the max capacity limit, it will shrink the cache to make the rooms for the new allocation. The last component is the memory pushback. It is the background daemon that runs periodically to check the system memory usage. Whenever system memory usage is go above some certain threshold, we will kick out the Velox memory reclaim process to handle spiky transient memory usage from the non-Velox components. That's how the overall Velox memory system works. The next, I will talk about the performance improvements we made to Velox memory system. I think the one key issue we fixed is the slow query wartime problem caused by the slow memory arbitration process. So to answer the problem, let's assume that one query start arbitration. So all the other queries which requesting memory arbitration have to waiting for the current arbitration to run completion first, because we're using a single log to protect the arbitration process. So if a memory arbitration process triggers spilling, it can be very slow, because at Meta, we spill data remote storage, so which tail latency could be very large. By observation, we find out a small selected query, which takes like 10 megabytes of peak memory and finish in 10 seconds, sub-seconds, is affected most. So if a small select query execution blocked by a slow memory arbitration process, its war time can be slowed down by more than 100 times. So to mitigate the problem, we first added reserve a small percentage of memory capacity inside the arbitrator to ensure each query has a minimum amount of memory to run. So this can help enable the small selected query to run through completion without interfering with the memory arbitration. But this doesn't fully address the problem. As for the medium-sized query, we still see significant regression in the query war times. So by observation, we realized that in Prestissimo, most of the arbitrations are local memory arbitration, which arbitration that only request reclaim the user memory from the requesting query itself, as it exceeds max capacity. So given that, we optimize this by parallelize the local arbitration execution. So we're using the read log for the local arbitration and only use the write log for global arbitration. So given the global arbitration, it rarely happens except the system is overloaded. So this largely solved the slow query wartime problems. And during this process, we also did a bunch of other optimization to make memory arbitration process more efficiently, like we will avoid excessive memory arbitration for concurrent requests from the same query. So before we start a new arbitration request, we will first to check whether the memory pool already has sufficient free capacity freed by the previous request, so that we don't have to start a new arbitration. And we also introduced the arbitration-aware driver yield control mechanism. So a driver will yield its execution if the associated query is under arbitration processing, so that we can avoid unnecessary blocking the driver threads. And we also did optimization to skip reclaim from the non-reclaimable query to avoid unnecessary tasks and pause and resume operations. So with all these improvements together, we effectively to solve the slow query wartime issues. To continue the memory arbitration optimizations, we redesigned the memory arbitrator internally to further parallelize the global arbitration with local arbitration without a single lock. As we see in the diagram, when a query cannot allocate sufficient free capacity from arbitrator, it will trigger the global arbitration by kicking out the background daemon called global arbitration controller to run. And the request itself just in the global arbitration waiting list. The global arbitration controller will manage the memory arbitration memory reclaim process, like setting the reclaim target and also select the queries to candidate query to reclaim memory. To parallelize the memory claim from multiple queries, we introduced the memory claim executor. It executed to do the actual reclaim from the query. When sufficient amount of memory has been reclaimed and returned back to free capacity pool, then the request waiting in the global allocation waiting list can resume with the granted capacity growth. And if the memory claim process is running slow compared with the memory request demand, then the global arbitration controller will decide to abort the query to quickly free up the user memory. To ensure we have a class-wide consistency, the abort decision will consider the query age, so that the multiple workers will abort the same set of queries. We also optimize a lot about this splitting process itself to accelerate a single memory reclamation process. So we did the following optimizations. We first parallel this splitting processing across multi-layers. We support to parallel splitting from multiple operators from the same query in plan node. And within the same operator, we also parallel spill processing by partition the spill data. And within a table writer, we parallel the multiple files writer flash within the same Hive data sync. And we also optimize the disk I/O to reduce the spill I/O cost to improve the performance. Like we apply the compression to reduce the disk I/O size. We also apply the right buffering to reduce the I/O processing cost within the remote storage client. And we also apply the read ahead on unspill paths to pipeline the spill file read with the unspill data processing to improve the spill queries latency. For the sorted spill use case, we leverage the prefix sort optimization to accelerate the spill data processing. The next, I'll talk about the optimization we made to the memory allocator to fix the CPU time regression that we see after Presto migrate to the hardware with higher CPU concurrency and larger memory capacity. Through analysis, we find out that this regression is caused by the high log contention from Velox own memory allocator. And Velox own memory allocator using a single log for space allocation so that you can strictly control the actual fixed memory allocation to avoid the memory fragmentation. But the problem that it could lead to high log contention with increased allocation concurrency and larger managed memory space. To quickly solve the problem, we decided to switch to malloc allocator, which has much better handling at high concurrent memory allocations. To mitigate the memory fragmentation issue, potential trigger introduced by the malloc, we rely on the memory pushback mechanism we built to handle to protect the server womb in some edge workloads. So next, I'll talk about the improvement made to the query womb prevention to help the LBM deprecation and QRT migration to Prestissimo. For those new workloads, we see some new we see the new womb patterns. Here I give some typical examples. Like for example, we see many queries in the hash join processing, and it is due to some edge cases. We don't have the spill coverage. For instance, there is a small time windows that hash build has finished build a table, but before the hash probe start probe processing, and when memory arbitration trigger at this point, we cannot reclaim from either side because both are in non-reclaimable state. So to solve the problem, we added a spill trigger inside the hash join bridge. And early this year, we started migrating Sapphire to Prestissimo, and we observed a new womb patterns that is due to pattern in the hash join. That is due to we don't have the spill support in the mixed mode execution. In the mixed mode group execution, the build side is ungroup executed, but probe side is group executed. To fix the problem, we are developing a solution to keep all the spill partition metadata inside the hash join bridge so that we can reuse the spilled build side data for cross multiple hash probe groups. We also did a lot of optimization, like fix the memory efficiency and data log fix around the parallel join build. So this enables us to run the hash join spill reliably and efficiently in production since the end of last year. The other common womb pattern we see both RBM and QRT is the table writer wombs. We do have a spill support for table writer, so by early stripe flush. But when those query wombs, each table writer has opened many files, and each file has only buffer a small amount of memory, so it doesn't reach the early stripe flush memory limit, so that the memory arbitration cannot reclaim memory from any of those table writer, even though each table writer could use up to gigabyte memory. This is already designed to parallel the table writer processing, but it's not a memory efficient. It can also cause many small files. And this only happens for the non-bucket partition table. The local exchange operator sit ahead of the writer pipeline will distribute the incoming data in the round-robin manners. So which means one table writer partition could be opened multiple times with one per each table writer thread. So we provide options for the user to fix this problem. So if configured, the local partition will partition incoming data using the table partition keys. So internally, the local exchange will maintain a map from the logical partition, table partition to the table writer thread. Initially, each logical table partition only assigned to one table writer thread. During the query runnings, if we see high buffering in the local exchange and the total query capacity is within a certain limit, we will scale up the processing by assigning some hot logical partition to more than one table writer thread. So these kind of help to achieve dynamic balance between the writer memory efficiency and the writer CPU process efficiency. And also starting early this year when we see some new WOM pattern in the Sapphire migration. So that is related to some queries with many stage. And the WOM happens right after the local memory arbitration finish. And by observation, we find out the reclaimed memory capacity has quickly resumed by the running driver thread from the same query. Because for the query with large number of stages, it has a large number of the driver threads running in parallel. So that to fix these timing-related WOM issues, we improved the memory arbitration process. Instead of to reclaim a fixed amount of memory, we fixed a certain percentage of the query capacity. This not only helps fix the WOMing problem, but also improve the memory reclaim efficiency for those large queries. For non-stable operators, one common pattern we observe in many different operators is we have inadequate output size control. The Velox driver execution framework has set output size limit, but initially many operators just respect the max number output rows, but they don't respect the actual output size. So we did a lot of optimization improvements, like for unset operator, hash aggregation, table scan, hash probe, and also extend the row container to provide faster row data size estimation to improve the accuracy of the hash probe output size control. And we also added row size estimation in nimble file reader to help prevent the WOMing for the table scan with nimble file format. The other common WOM pattern we found in the LBN and the QRT is due to the memory efficiency of the columnar page serializer used by the partition operator when dealing with wide shuffle, which has a large number of column streams. And we did a series of optimization from initial to optimize to support fine-grained allocation within the stream arena to avoid the unused memory allocation within the Presto page serializer to eventually support the row-wise shuffle. This significantly reduced the peak memory usage of partition output operator. The other common WOM pattern we see in the table scan WOMs, that's due to the query just run too many table scan threads, and each table scan thread uses a significant amount of memory. To mitigate the problem, we provide option for user to scale up the table scan processing and a certain memory budget. With this all optimization together, we effectively to prevent the WOMs in persistent production and meta. So we will also continue to investigate and fix new WOM patterns when onboarding new query workload to Prestissimo. The last I will talk about the memory pushback mechanism we built to handle the non-Velox tracked memory spike. And the memory pushback is implemented at the background daemon we call the product memory tracker. The product memory tracker will proactively track the system memory usage. So whenever the system memory usage go above some certain threshold, it will kick off the Velox memory reclaim process. It will first to reclaim the unused memory from the cache. And if it's not enough, it will go ahead to abort queries to free up the used memory quickly through the memory arbitrator. And by adopting the memory pushback mechanism, plus the throttling mechanism we built for remote storage client, and the flow control mechanism we built for the HD-based shuffle together, we can effectively to handle the transient non-Velox tracked memory spike. Yeah. That's all I have today. Yeah, thank you.
We have time for like 1 or 2 questions.
Thank you. Is there any fairness process in when it comes to killing the query due to OOMs? Because I think you were showing that like if the query requests some memory, it would be killed like in some cases. But could it be the case when you have multiple queries that are, for instance, running, let's say, and using like 10 gigabytes, but there is another one which is just using 2 gigabytes, but is requesting memory, but it cannot get it? Mm-hmm. Will this query be killed, or some other offender, like or highest offender on the worker will be killed?
Yeah, so when we abort the query, we consider the query age, but we actually have a certain threshold because we don't want to, kill some like young queries which has a small amount of memories. We actually want first we see how much we have a threshold. We put the query in multiple buckets based on the current memory capacity. Within the same bucket, we queue based on the age. For example, if the threshold, if we starting from, suppose like the query with 10 gigabyte memory is probably in the highest bucket, we first to abort from those queries. So we will choose of those queries first, and then we go to if we cannot reclaim sufficient memory, we'll go to lower bucket to kill the 2 GB memory. So it's most likely that we will first to kill the memory, the query with 10 GB memory.
Thank you.
So you mentioned you're using JMalloc to do all the memory accounting now. Are you using internally the allocator for the memory or the malloc allocator? So JMalloc becomes more of a usage there, or how do you deal with linking just JMalloc into the final library?
So what's your question?
So you said you're using JMalloc to
Yes.
try to reduce the fragmentation and things like that, but
We're not using JMalloc to reduce fragmentation. We're using JMalloc for the high concurrent memory allocations. And to mitigate the problem, because the Velox own memory allocator is good at handle the memory fragmentation, and we are still using that for some like internal like directory queries, which are small queries. I mean, use case. We're still using the JMalloc. We're still using the allocator. But for the parallel batch, we are using the JMalloc because we are running on some high concurrent hardware platform to handle high concurrent allocation. So instead of to optimizing our own memory allocator, we choose to using JMalloc to unblock the CPU time regression.
okay.
Maybe time for one more. Pass it back. Oh, sorry, back.
Yeah, I actually also have a follow-up question for the JMalloc one. So you mentioned in one of the slides that when you have fragmentation, when you observe high fragmentation from JMalloc usage, you will apply pushback mechanism. Like, can you talk a little bit more? How are you doing that?
So basically, the pushback will check the system memory usage. If the system memory usage go above some certain threshold, then that's very likely the topper or the host will kill the process, right? So we need to free up the memory. So basically, we will kick in to reclaim memory from Velox. Like first, we reclaim memory from the cache, and then reclaim memory from through the mem arbitration, just abort the query to quickly reclaim the used memory. And also at the last, since we now using JMalloc, we also add to call release on dirty page from JMalloc. But very recently, we realized that operation very expensive, could take like a minute in some worst case. So the pushback basically free up the memory to back to the system, and so.